right, so welcome back everyone to the last session of today's workshop. So there will be a total of 3 talks in the next session. First of all, again by Christian, talking a bit about his research on model predictive control. And then I will be giving a talk more on model learning and identification of the models that I talked about earlier. And finally, there's a talk by Miguel, which he's going to be talking a bit more about close range navigations and some solutions that also involve data-driven methods. All right, so without further ado, so Christian, the floor is yours.
Okay, thank you. Okay, so I briefly wanted to present model predictive control in the context of autonomous underwater vehicles, which is something that I focus on in my research. Okay, and for this, I want to give you an overview about what is model predictive control, and then give you an example of an application in underwater robotics. And let's just start with that. So what is model predictive control? The basic idea behind model predictive control is that control actions are chosen by predicting possible future trajectories and then trying to follow the optimal one. So model predictive control is a feedback control, fits into a control architecture like any other controller. This is shown here. It is based on mathematical optimization, so it belongs to the category of optimal control. It uses a model to predict the future states of the system, so like a simulation model. And one thing it does, it can handle constraints inherently. So, and this is quite important for control. If you're thinking about input limits, thruster limits, of kind of thing, then this can also be incorporated into the control law. So we're going to talk about a little bit about this later. Okay, I do want to give a brief overview about this, but as I know you get another workshop more dedicated towards optimal control and LQR, so a lot of these things will show up again. So I will just go briefly over this. But yeah, it's important to give you an understanding. So essentially in the to predict future states, what we can do is we can use a discrete description of our system dynamics, so a discrete system model, and this can look like the equation shown here. So we have some x at the time step k plus 1, so that is sort of like the next time step, and this will be a function of the states at the current time step, x of k, and an input vector u also at the time k. So with this, we can iteratively compute the system dynamics at always the next time step, the next sampling interval, and those iteratively calculate a whole trajectory. So what we'll have, so for example, if we have an input trajectory, we can calculate all future states. That, of course, is provided that we know the current state. Okay, so this is sort of like the prediction part already covered. What we can do now is we have to essentially calculate a whole bunch of these trajectories, and then we evaluate them based on some cost function. So we can use a quadratic cost function for this, where we put like a cost both on the states, so and the input. So the states here are, so with this, of course, like any state that is not 0 has a cost. So you can also think about this as a state deviation, say. So maybe x is your error that you want to minimize. Works in the same way. But yeah, okay. So here, let's say we want to regulate all our states to 0. Then this is the appropriate cost function. And we also want to penalize using a lot of input. And this is these x and u are for all x and u in their respective trajectories. So similar as before, I mean, this we've talked about this like 2 times already today, so this should seem somehow familiar. We have again weight matrices where we can sort of decide how much we want to penalize the use of input and how much we want to penalize the use of or like the state deviation. And according to this cost function, we get then the optimal trajectory, which is the optimal trajectory that leads to minimum cost. So that is the minimization part. We can extend this towards constraints. So that is one of the strengths of MPC. We can handle constraints explicitly, which means, for example, state constraints. Maybe we want to allow only a certain set of strains. That could be we want to discourage large or not allow large velocities, or say we want to avoid certain orientations or certain positions in the water, column. So those kind of things we could constrain here. And a similar thing can be done for inputs. I mean, we've already talked about input constraints today quite a lot. And another interesting thing you can do very simply is input rate constraints. So seeing that thruster dynamics are usually quite a limiting factor. So you can actually say that you only want to change your input rate at with a certain or at a certain rate. I put a constraint on that as well, so thereby sort of like approximate the dynamics behind it without having this actually in the model. So, and if we put this then all together, we can formulate an optimization problem like this. So might look quite a bit in the beginning, but essentially what it is again, we over an horizon of n states. So we predict the next n states. And for these next n states, we want to formulate this cost function, again, as a quadratic function of x and for x and u. And then we have a bunch of constraints. So the first one is actually the most important. It is our state equation. So this is how is our discrete state description. And so this is essentially the prediction part, and the others then are constraints on states, on inputs, and on the input rate, for example. So this is can of course be extended arbitrarily. The problem is that these are generally nonlinear and non-convex. So, and in a general case, this is very, very difficult to solve, or maybe even impossible. A common way to simplify these is to revert back to quadratic programming, which is very well understood. So here the cost function can actually stay the same. We need a quadratic cost function. We already have one. And but we need to linearize all of the constraints. And that means essentially that the allowed states and the allowed inputs must be convex sets, as given here. And we also have to have a linear state equation. That's actually the largest drawback of this approach, that we have to linearize our state equations, and that's of course only valid in a certain range. But yeah, it's a very common approach because now we have a quadratic problem that can be solved efficiently. Yeah, so then there's one thing missing to the full MPC algorithm, which is the receding horizon. As said, like we try to predict the next n steps, and what we get through the optimization is an optimal trajectory over these n steps. But what we do not do usually is we do not apply all of these n steps as the input, but instead we only commonly only apply the first one. So only at time k we apply the input, the optimal input from the optimal trajectory at time k, and we disregard the rest. So and then we repeat the entire thing at the next time step. So that is the basic idea here. And by that we, of course, at each time step keep looking further and further into the future. And this actually is what introduces state feedback. Okay, let's come to how we implement this on underwater robotics. So first of all, maybe let's try to motivate why we want to do this. There are many good reasons. So as I said, like thruster constraints can degrade performance in traditional control systems if they are not considered inherently. And that is, that can lead to limit cycles, for example. And so it is desired to represent those also in the control law. And then, of course, we now have the possibility to get good models, and we actually want to use them and want to be able to exploit them. And that is something that MPC can do, and it can also handle coupled systems. So there are quite a number of advantages that make them applicable to AUVs. Another interesting thing is that AUVs are typically characterized by slow dynamics. So, and since MPC is computational costly, high frequency control is rarely achieved with MPC, at least for high, very high, very long prediction horizons and very high system order. And so here it is should be much more easily applicable. But one thing that we use it especially for in research, and also done by a master's student of mine, is to consider it as a disturbance, for a disturbance preview. So that means in some cases we are able to predict disturbances that are acting, or like external forces that are acting on our system, for example, by a moving manipulator. So if the manipulator is controlled by an operator, or like just follows a given trajectory, then we know in advance how it is moving, at least to some degree. And why not use this already in the control law? And we can simply do this by including this as part of the system model. And so like a disturbance caused by a manipulator could be something like a ramp seen here. Of course, it's a simplification, but so we give some sort of torque on 1 degree of freedom, and we try to compensate that. And this is what has been done. So here with based on quadratic programming and a linearized model of the system, we'll essentially try to keep the vehicle in a neutral orientation. And at 5 seconds, we apply this disturbance, and what we can see here is like how different approaches here lead to different results. So in the open loop case, this disturbance is actually quite large and leads to a deflection of about 40 degrees. And if we have MPC but without preview, then we can lower this already to about 5 degrees, which is not perfect, but it's the MPC here itself is not very aggressive. And if we then include the preview, then we can see that we can actually very much get rid of the disturbance at all, and what we're left with is essentially caused by the sampling intervals. If we look at this in a bit more detail, then we can really see what is what's going on. So at 5 seconds, this disturbance is placed on the system. So before, and even before that, we see that like at 4 seconds even, the vehicle starts to prepare, starts to react, because the minimization routine tells it, okay, it's better to accept a small deviation early on to reduce a large deflection later. So, and you get like a little bit of this in the beginning. Before 5 seconds, you get a little bit of oscillations that try to prepare for this disturbance. So it's what you expect, and but I think it's still quite interesting. And MPC is in some sense a very intuitive control law, which I think makes this this example can also show or makes this clear. It is it's a control law that in a way when it's done correctly, it does what you expect. It looks ahead, similar to a human driver would drive a car. It looks ahead and not only looks on the road below the vehicle. Okay, that was a short excursion into MPC and some of the preliminary results that we have done. Few questions? Okay, I see 2 questions. Sasan, please.
Yeah, just wondering if you use the same approach for providing trajectory as part of the planning component. So using MPC, you come up with trajectories, right? The trajectory.
Yeah.
So that could be also used as for the planner to follow that trajectory.
Yes. So it in a way it is a hybrid of control and planning, at least a very local planning. It's not an efficient approach for global planning, for planning along trajectories. There are better approaches, more efficient ones. But yeah, in some way you're right, and it is also planning. And yeah, it is very useful for following a planned trajectory, because you know, if you have a plan, it's like having a road. You know, when you drive a car, you can see the road, you know where it's going. So at least the next 100 meters or so. So you can include this in the control and anticipate a change in direction early on, which is maybe especially interesting if you have thrusters with slow dynamics. So then you might need to prepare such a situation earlier on, or you would probably want that to avoid overshoots, to avoid deviating from the trajectory overly much. So it's quite a useful tool to also follow trajectories.
Okay, thank you.
It's also useful if you already deviate from a trajectory to bring you back on the trajectory. Yeah. I think there was another question.
Yeah, hello, Frank. No, I think this is Christian. Can you hear me?
Hello. Yes, I can hear you.
Yeah. So my question is more regarding when you're running MPC online on the AUV, what kind of processing power are you looking at? I mean,
so the simulation that I showed you were done actually not on AUV, but this was a simulation done in MATLAB some time ago. You can see like with a horizon of 2 seconds and a sampling time of 0.2, it's not very, it was not very fast. But with modern approaches and modern libraries, it can be much higher frequencies can be reached. But I don't want to like don't pin me to a certain number here, please. But yeah, it should be well enough to control the vehicle with modern computers, of course.
Okay, so we are looking at something like a full-blown processor rather than a microcontroller, which we normally use on an AUV.
Well, yes, it's certainly. I mean, there are also hardware accelerations that might be usable here. So maybe not relying on a full processor, but yes, solving these problems, especially when they are not strictly convex, then it is getting, it is assuming quite some energy.
Okay, thanks.
And computational power, yeah.
Okay, if there are no more questions, then we will move on to the second talk, which I'm going to be giving. So thanks again, Christian, for the very interesting talk.
Welcome. Thank you.
All right, so hopefully you can see my screen. Okay, so in this talk, I'm going to be talking a bit about system identification of underwater vehicles and more like model learning in the second part, which I did most of this work during my PhD thesis. So hopefully give you an overview also like about the comparison between classical system identification and more advanced or data-driven methods. So it's going to take the following order. So first system identification, then model learning, and then I'm going to touch a bit also on online learning and model adaptation. So first of all, like if we just recall the equations that we have, I think you are now a bit bored to death from these equations, but if you basically just expand them and arrange them in a way that is like as if we are having a linear system, however, so y are like all of the independent variables. For example, they could be in this case the tau or the actuation. Theta would be all of your unknown parameters that we've seen before, like these added mass elements or the drag elements or all of this kind of stuff. And then x here basically is just a matrix that you can construct by just concatenating all of these nonlinearities in the system that you have. For example, acceleration, velocities, whatever model you choose. For example, for the damping that you have, you can align them in this kind of vector form or this kind of matrix form, which would be here in this case m by p. So basically, m is the number of dimensions that you have in this case, which is 6, and p is the number of unknowns that you have. So all of the parameters in your system that you don't know is p, basically. And then theta is this vector that represents all of the unknown parameters, which you can also just concatenate all of the unknown parameters in such a way. So like the added mass parameters, the damping parameters, and whatsoever. So this is like you have p unknowns, for example, and so if you just do this multiplication, you just recover back the original system. So how do you want to now identify that? This is a very simple problem then. If we just have a certain data set composed of, let's say, velocities, accelerations, and the wrenches that we have of n samples. So if we construct a matrix basically by just concatenating down in row-wise all of these samples all the way down to n, we will have the so-called design matrix. All this is all of the data that we have. These are like the independent variables in this case. And let's call this matrix x hat. If we concatenate all of the samples of the wrenches that we have in this case, I mean, you could also do it the other way around. If you want acceleration to be your independent variable, so you're solving for the forward model, this way we are solving kind of for the inverse model, but I mean, in the end, it doesn't matter. And then your sum of squared errors, so is also here a simple optimization problem that you want to have to minimize the error between the sample that you measure and the prediction that this model here, so x hat theta would do, and you want to minimize that for theta, right? So this is the simple least square algorithm. So we can write this in the following form, And yeah, the goal here is to get the argmin of j of theta with respect to theta. So the simplest solution for that, I think Christian probably mentioned it before, is the Moore-Penrose pseudo-inverse. So since this matrix X is not full rank matrix because the number of samples is not equal to the number of unknown parameters, so we transform it into a full rank matrix basically by multiplying the transpose by the matrix itself. Then we can invert it in this case. Otherwise, it will be an ill-defined problem. Now, a very important thing here is that this is supposed to be so that mostly this kind of problem is overdetermined. So if you have more number of samples than numbers of parameters, then this is an overdetermined system, which is better to have than an under. So if we have less samples than number of parameters that we want to identify, then we will start getting bad results. So again, so this is just, again, an approximation. Now there are other ways of solving or other least square methods. This is the simplest. There is something called the total least squares. So instead of using the Moore-Penrose pseudo-inverse, you could do a singular value decomposition of the concatenation of your samples, so x and y in this case. And the single value decomposition will decompose your matrix into three matrices. And then if you take the V, or the called unitary matrix, and basically just taking the first P elements of the last row will give us these thetas scaled by the last element. For proof of this method, you can check out this. I think it's a little bit too much for this. Another method is recursive least squares. So that's also, it's the same way basically in the end of doing the same thing. There are some differences between those methods, like ordinal least squares, for example, takes into account noise in the targets, but not noise in the inputs. However, these two methods, recursive least squares or total least squares, will account a little bit or try to correct for noise that you would have in both samples. So recursive least squares is a little bit very similar to what a Kalman filter is. So first of all, you have a covariance matrix P, and then given a sample, you propagate it forward. R is also here the measurement noise. So you usually set it to a fixed kind of matrix. So to try to model how much noise you expect in your system. Then you calculate this rate of change of the parameter theta, which is similar to a Kalman gain. And then you just update your estimate and then update the covariance matrix. And then this basically could also be done online. So you don't need the whole data in one go, but you can do it like when samples arrive sequentially. So this is how we could identify. So of course you need to collect data. You need to find a way to capture this ground truth of your robot or data that you have. Now the other part of the or another paradigm is basically model learning, which again, if I remind you a little bit of these equations, so we will assume that tau here is also a function of u, such that u are the inputs that we give whatever actuators that we have. And we've seen before that f is also could be a nonlinear function and could also have uncertainties. So for example, the models that were presented, like if your thruster is close to the body of the vehicle, you will also have an interaction a little bit there, which is quite hard to capture. You could also use some kind of computational fluid dynamics approaches to try to estimate that. But what we will do here is we will consider it as an unknown function and then try to estimate it using just generic function approximators. So we consider, again, so the forward model would be a nonlinear function, like v dot is the target that we're trying to get, or the acceleration is a nonlinear function with respect to the states v, the velocities, the wrenches, and the rotations. Or we could directly write it as a function f. So this would basically embed the whole nonlinearities into one function. And again, so the idea is just to use some generic function approximation to try to fit that model. One of the functions I'm just going to mention here briefly is support vector regression, for example. You could use anything else. You could use neural networks. You can use Gaussian process regression. I chose this here because it's simple, and there are some properties that I'm going to use later, such as the support vectors. So the idea is quite simple. Instead of penalizing all of the data, the error of all of the data, we just penalize samples that are outside of a certain threshold that we call this epsilon. And this function also uses a so-called kernel trick. So you transform your function from a linear to a nonlinear function by having this mapping phi, which kind of maps your input features into like some higher dimensions, and then you can recover the nonlinearity there. However, so if you take the inner product of here xi phi x, you will have a so-called kernel function. I think if you want to ask me a little bit about that later, so it's just a bit roughly. So if you've taken any machine learning course, you should have went over these kind of stuff. So the kernel function also has lots of properties. And exactly, so this is, again, the loss function that we're trying to optimize here. So do we call this epsilon insensitive? So everything inside of this tube we don't penalize, and otherwise we just have an L1 loss if it's outside. So there's, again, a big mathematical formulation I'm not going to get through now. So again, so this function is, or this method can approximate nonlinear functions for us. So here's the approach that we try to do here. So one is following the parameter identification approach. Here we selected two models that I talked about earlier. So this Gertler and Hagen model and McFarland and Whitcomb from 2013. The reason I selected them because they were the most parameterized classical models or physics-based models, let's say. And on the other side, we have three versions of a support vector regression. So the kernel basically is just what changes here. So the so-called radial basis function kernel is, you think about it as you're just trying to estimate the correlation between two samples using just the bell curve or the Gaussian curve somehow. And so you can always scale the width of this bell by choosing one parameter, which is like multiplies then this Euclidean distance if you have multiple dimensions. However, you could also have different weights between the different dimensions that you have. So squared exponential is just a generalized form. So instead of using just Euclidean distance to measure the difference between two samples and then calculate the exponential of it, you can scale that with a matrix in the beginning, like of weights. So, or it's also known as Mahalanobis distance. And since here we have kind of two different inputs, so or two kinds of inputs. One is velocities, one is torques in this case, or RPMs of thrusters. There's another one here that instead of having for each degree of freedom or for each dimension a different hyperparameter, because these you have to tune afterwards, I just used two. And here's a little bit the data acquisition. So I used in this case this vehicle diagram. I'm going to show it to you later. So it has 5 thrusters in total and 3 thrusters for like planar motion and 2 thrusters for like pitch and depth. So I stabilize pitch and depth, and then only in the XY plane. You can see here I give it kind of periodic and band limited excitation. So the idea of that is based on a paper for identification of industrial robots. So to cover kind of the whole data space or state space of your system or whatever this can achieve is if you give it a finite Fourier series with like periodic different periodicities, you could try to cover kind of every combination between the dimensions that you have. So on the side here, you can see a little bit snippet of the data set that we have. So here there's like velocities, RPMs of the thrusters that we can measure, and accelerations. So the red is the targets, velocities are the blue ones. So if we take that, plug it in all of these systems that we've seen before, pass this also into a k-fold cross-validation. So the reason for that is to try to find also the best hyperparameters that would perform here. So the idea is that you take the data set, first take a test set apart and then train with the rest. Then the second fold, take another part of the data, then train with the rest, and then in the end do this on. And then in the end just get the average or of those, or you can also plot like a box plot that gives you the difference. So the idea behind this is also like to see how biased each model is. So you can see here a bit the performance, like these are the two physics-based models, so got Hagen, Whitcomb, McFarland, and these are the two support vector regression, three support vector regression models. The metric here is coefficient of determination, or R2, which is basically just 1 minus the mean squared error multiplied, divided by the variance of the targets, just to give us kind of a unified metric. So if you are close to 1, then your prediction follows exactly the data. If you are 0, then there is no correlation between your prediction and the data. And if you can also have negative values, so this is mean bad correlation between the prediction and the actual data. So I mean, here you can see the differences. So obviously the support vector regression that has more hyperparameters perform better than any of those, even though here, for example, the difference is not that big. But you can see here, for example, this big standard deviation means like if you train on part of the data and test on another part, you will have a little bit more bias. So your model a bit overfits somehow, or no, sorry, in this case it underfits. So if you train with part of the data and then let's say take the first fold, you have a good performance. However, if you try to take one of the others, then your model doesn't perform very well if trained by some other parts of the data. So yeah, this is part of these results. I mean, if you want a little bit to go a bit in more details, here's a paper I published with one of my colleagues. It's a bit old paper, but still I think worth mentioning. So here's another. Actually, before that, let me show you a bit more results. I didn't include them in these slides, but I have them somewhere else. Yeah, exactly. So I took those two of so the best performing model from the model-based approach, or from the classical, let's say, parametric approach, and the best SVR. And then I used the same observer filter that I showed you, talked about a bit earlier during the docking. And here's one experiment we also ran with a robot in the lake here near the university. So here you can see a little bit. We started here, we ran like a lawnmower pattern. So these are GPS, so the red are GPS measurements, just for ground truth. And traced this lawnmower like, I don't know, 100 meters in each direction. So it's like overall traveled for around 800 meters, and then here's where we dive up, and this is where we get the first GPS fix. So you can see here with the full-blown observer or Kalman filter, like with all the sensors in, so IMU, DVL, and the depth sensor, it performs kind of quite well, especially that when we go up, like we directly go where the GPS fix is. And we tried basically to, like later on in post-processing, to cut off the DVL, for example, on the curves, which are the hardest part. So everything you see here in green, we just intentionally kind of stop the DVL from working. And these are the results that we have. So this one here is the results where the model of, or like this WM or Whitcomb-McFarland model, this physics-based model, this is how it performs compared to the support vector regression model, and this is how this one performs. So you can see a little bit, just kind of also a proof that if you try to try to take this model that we learned, put them in some practical application, how the difference would look like. So go back to this slide. So another thing that we tried to do, so before we were just taking any method for like function approximation and then just from scratch trying to learn directly from the data. However, one thing that I was asked, like, okay, what do you do with all this knowledge that you talked about? Why do you throw it away? And since we have physics models that kind of perform quite well in the end, okay, we have a bit better approximations using, say, support vector regression, but what about combining the two? So one approach I had is first to actually learn the residuals. So first take a physics-based model, take the classical model, and identify that, and then learn the error between the data and whatever the model produces. As if, in another sense, we are trying to estimate this part of the equations, which is like the unmodeled effects that we still do not kind of capture with a physics-based model. So that's one approach. Another approach, which is a bit relies on the idea of transfer learning. So the idea here is I took this physics model, plugged it into a simulation, and then just ran the simulation and collected more data. And then basically what happened here is that I took the simulation data, which kind of represents, in a sense, or gives us a little bit closer, something close to reality, but not fully, and then pre-trained an LSTM model. And the reason why I chose to have a recurrent network to also, the idea or the logic behind that is also some of the things that I talked about in the added mass earlier, is that this memory effect that you have that we don't really capture in those equations. So I thought, okay, why don't we use like a recurrent network where every time the output is also fed in as part of the features in the second step. So so one of those is this long short-term memory networks, where I pre-train it with the simulation data set and then fine-tune it on the real data. So by pre-training with the simulation data set, you kind of warm start the network to have a closer solution to reality, and then fine-tune it on the real data to try to predict, to have a better prediction, basically. And here are some of the results that we have. So I'm just going to explain it quickly. So first thing to the left here is purely the physics model alone, which is similar to what we had earlier. Followed here by, so here again is the R2 score, followed by the support vector regression trained from scratch, so without any physics model in between. And here combining the both, following the first method. So basically first identify the physics model, then learn the error. And on this other side, you can see, so if we just train the LSTM only on simulation and try to predict directly on the real data, we get actually not a very bad prediction. I mean, not very good, but not very bad. If we also train the LSTM just from scratch, only on the real data without any simulation, it performs well, but actually here the parts, both of those actually kind of are a little bit better. But you can notice here that the best model basically is the one that when we pre-train this neural network with simulation data and use this idea of transfer learning, we just fine-tune it on a little bit of data from the real experiments. And you can see here a bit the learning curve. So we took this pre-trained model, and then instead of just giving it directly the full number of samples, you can see that already, like just from around 2,000 samples, it kind of can achieve a really good performance here, like starting from nothing and then increasing up the number of samples and just trying to predict every time. So like for each degree of freedom. I think I can talk briefly also a bit about the online learning part. If we have the time, I can talk about it a bit briefly. So this is also was one part of my PhD research. So the idea here is to, I mean, we have now all these online, all these models trained they perform quite well. However, everything is still offline. If we have a model, we take it, we, let's say, collect data in one experiment. Now we move into another environment. Everything changes. So let's say one of the reasons could be like if we change the structure of the vehicle. So here's this vehicle Dagon, that the way it was before and the way it is now. Well, actually now it's like this again. So a change in structure means a change in the hydrodynamics. Biofouling, if you want to leave the robot for a long time underwater, could also induce more drag, for example. Like here's one of the gliders at the beginning of a mission, and then here after like a couple of weeks, you can see how all these barnacles are collecting on it. Or just the changing environment. Like if you just move from one environment with higher viscosity to an environment with lower viscosity, all of your dynamics change as well. So this is kind of what motivates to adapt online the dynamics of the robot. So here's like one concept I also came up with. So the idea is quite simple. So we have a data stream where like all of these data are kind of online. Let's say whenever we have a full vector of like all of the samples that we want, we pass them in to this framework. So first of all, there's an including node that acts as like a gate or a filter. So like, first of all, to prevent redundant data by training on redundant data and then making the model kind of overfitting or specialized only on parts of the data. And on the other hand, to spare a little bit computation. Then this part here is an online learner. So I also took an incremental support vector regression, and which kind of at every time step you update incrementally by the data that you have. And here there's a so-called sample collector I'll come to in a second. Then from here onwards, we take the support vectors that were generated. We remove some of the outliers to reduce sensor noise. And then we pass it to a forget node. So the idea, why do we want to forget parts of the data? Because at some point, either your memory blows or your system tries, or your learning method tries to fit two different models in the same time. So you need to kind of forget all data, but you need to make sure that you are not forgetting important parts of the model that you have. So we try to sparsify these, since this is a memory-based learner, so you keep the samples or you keep the support vectors. We can perform, for example, some analysis on these samples to like try to keep a little bit of an even distribution among that, and controls also a little bit the memory that you have. And then at each step we collect the samples together with the including node and then pass it again to the learner. And here's a bit the scenario that I tested. So I took this vehicle with the default setup, let's say. Then we transitioned here. We added, for example, a payload like a sonar to change a little bit the drag. So this induces way more drag. And then the last part is we took this front hydrodynamic hull to also add more drag, for example, and change the geometry. And here's a little bit how the results. So also on this side, R2 score, and on the x-axis is time. You can see here is the first shape. So this error kind of, or the performance increases to a point that it like saturates and like you reach quite a good performance after some time. You can see here that when we transition to the second part, this performance drops kind of, but then recovers quite quickly. And same thing happens here, like when we move into the third configuration, it also drops and then recovers. If we compare this to not having, so only having just a support vector regression where we always delete, let's say every time your buffer is full, you always delete the oldest sample, this is what happens. So your performance kind of degrades quite badly because we are not keeping, let's say, kind of a balance in the support samples that we have for these methods. Yeah, that's most of it from my side. Again, if you want to read a bit more about it, there's a paper I published in ICRA. Talks a little bit more in details. How do I do all of these kind of conditions on the learner? So yeah, thank you very much. And if there are any questions, I'd be happy to hear. Yeah, please go ahead. I think, Maya, you're still muted. Okay, now you're better. I unfortunately cannot hear you.
Hi, can you hear me?
Yes, I can hear now.
Thank you. Thank you very much for the most interesting and inspiring workshop. Actually, I do really enjoy it for the this last session. And regarding my question, I just wanted to know about this forgetting node that you mentioned. What sparsification model did you use in your model sparsification? What kind of model did you use in your project?
So basically, I was trying to strike a bit of a trade-off between how old a sample is in my buffer and how frequent, or like how many neighbors are next to the sample. So the older the sample, the higher the score of it to be thrown out, and the higher the density. So I also use like here some kernel density estimation on the samples that I have, and then so samples with higher density, this means that there are samples around it that is giving me the same information, so that's more likely to be thrown out. So it's a little bit an ad hoc method, let's say, but it worked.
Thank you very much. It makes sense. And also, I have another question. I found your PhD thesis right now. I searched it in Google. I wanted to know that did you publish anything related to your simulations and your data and results for your PhD project in public, or is it acceptable? About the results and the approach, the methods that you employed in your PhD thesis?
I mean, the approach are definitely in the papers that I just mentioned here. So there are.
Oh, you're just so it's not.
But if you're talking about the code and the data, if you like, I can also provide you those. They are quite due to put them on GitHub. I think I'm just being a bit lazy about it.
Oh, thank you, thank you. I'm such a thanks. Thanks again.
Any other questions? All right, so are you there?
Yeah, sorry, I lost the connection, but yeah, I'm there. Can you hear me?
Yes.
Yeah, okay, I will share my screen. How much time do we have? Not that much, right?
I was hoping that we could finish by 5 the most, like also including a little bit, like, I don't know, 10 minutes tour later in the basin. Yeah,
I'll try to be fast. I mean, at the end it's only an excursion of everything, other stuff that we're doing. So yeah, I'll try to be not long because we've been hearing a lot. So that's, I hope it's not gonna be that dense. Interesting anyway. Yes, I'm gonna be talking close range navigation in docking applications mainly, but also we make an excursion to underworld perception, which is also important for docking and for other applications, of course. So you see already these videos, so I will go through very fast. Why is important docking? Well, as we mentioned also this morning, we also use, we're going forward to subsea residential AUVs, which means that long-term AUVs has to stay there longer because it's much more efficient and economically speaking, much better. So for example, we have Flatfish that has his own docking station and can make some exploration and then come back and recharge batteries and be ready for the next mission. But also might be that we have no human intervention at all in, for example, the applications that we're doing in space, which then often, obviously, we have to dock sometimes and give this information to the base station, ground station, which then is send it to the Earth, for example. Other applications, robot-robot interactions, you already see this video, in a sense that might be that we have a couple of robots making underwater mission and we want to change some samples or information. So it might be that they have to dock somehow. And also this other application, Cuttlefish, that it has been already by Christian presented. So it has a couple of manipulator arms which can dock on the platform. So it then provides to the operator that can be remotely somewhere on the world to manipulate the other manipulator and see also what the Cuttlefish is seeing with the cameras. So there are some applications for docking. And we already mentioned that mostly, Bilal said before, we're using vision-based approaches with markers because they are very accurate. But as he already told us, not always is that nice, as in the basin that we have. So for example, we are in the lake, in the underwater, and when we find the docking station somewhere, we cannot see almost anything. And if we're far away, like 2 or 3 meters, we cannot see the markers anymore. So it's so distorted that it's very difficult to see. So it's difficult to dock because it's difficult to see the markers. So we might use other modalities to cope with those. Of course, we have maybe models, and we have the control chain that we haven't seen, which we have an observer that we can then figure out where we are. But what would be nice to have all the perception somehow to localize our docking station. Because as I said, in the vision, we're lacking robustness in demanding environments, in this case, in turbid waters and so forth and so on. Another very common way of perception underwater is with sonars. And that's because underwater, we have a very nice perception with acoustics. Here we can see the camera and at the same time the forward-looking sonar. And we have the range and the bearing of the object. And also with the shadows, we can even identify sometimes how high is and also how depth we are and according to the position. So that's interesting algorithms that one can use. And of course, here we cannot see anything, but here already see some objects. So you have much more range with sonar than with camera, obviously. But it has also other problems, definitely. So the accuracy is lower. It depends also on the frequency of the sonar. If we have high frequency sonar, we can have a higher resolution. But then we cannot go so far, you see. And lower, then you have the much resolution, but then you can see much in a higher distance object, so to speak. There's also another problem, and is that we're using acoustics, and the speed of sound, it changes underwater, mostly in the sea because of salinity, but also temperature. So it's something that you always have to count on, that you have always inconsistency and uncertainty on your measurement. And there's always multipath characteristics, which means when you are very close to the docking station, and Bilal already mentioned that, then you have multipathing with your own docking station, which then distorts also the image and is complicated in very close range. So we might need another modality. And as Bilal mentioned, we are experimenting with magnetism because first of all, the magnetic field is not disturbed, but all these effects like turbidity or multipathing, there's nothing with magnetism. And also because, as Bilal said, most of the docking stations, they are with ferromagnetic materials, also high magnetic permittivity materials, which then it disturbs the magnetic field and has its own magnetic signature. And then we can use that maybe to localize ourselves. I will show you that quickly, how that works. And that is mainly a work that has been done in a PhD of one of our colleagues, like Christensen. We'll put that in the references. But we are developing that further in Triple, which is a project that you might look up. And also, we make a short excursion for what we're doing to use these two modalities, because the two has the pros and cons, and how we can fusion that with multimodal learning. We're doing that in DeeperSense. It's another project, which you can also look up if you're interested. So let's go, first of all, to the motivation of distortion of the magnetic field to use it for close range navigation. So we going here through a corridor with a robot, and we have a magnetometer, and we see these columns here and here. They obviously have a steel inside, so it distorts the magnetic measurement. We can see here when we were close to this column, it distorted the measure of our magnetometer, because obviously this soft iron effect that is producing the steel is this distorting the Earth magnetic field. Here it's happening again. So as you see, it does have, every event column has its own magnetism signature, so we can even identify which column is which, and also obviously the position according to the model of the AUV and the inertial sensors that we're using to position the AUV. So the thing is, okay, we have two columns here, definitely. So we can position that. Imagine that that is our docking station, for example, right? And of course, if you have a very, like our floor, if you have many columns and many artificial structures that are high magnetic permeability, you can even use that kind of a slam. And actually, there is a nice, interesting paper and a method that's called MagSlam, which use this measurement to make kind of a slam of your floor, for example, which you can use obviously for navigation. But let's go to the problems, though, because in the same way that the docking station has his own signature, a magnetic signature, the robots has that as well, because it has body and has some materials that can distort as well the magnetic field. And the problem here is that they are not static normally. So you have motors that it changes, and the distortion of the motor changes depending on the RPMs that we're having. But as well, if we have a manipulator that is moving the joints, the magnetic elements are changing all the time according to the magnetic field, to the magnetometer, which also then will feel that distortion is different. And of course, we have a lot of electronics that can be very compact, sometimes in close to the sensor, which also produce electromagnetism distortion, like current flowing through the electronics, but also some oscillating fields that happens with the transistors and other switches. Why normally, when we want to measure the magnetic field of the Earth very accurately, like in these two cases, these two satellites, one from the European Space Agency and also from the NASA, they are trying to put the magnetometer as far as possible of the satellite. So for example, there's this boom here, there's a couple of meters, and the same here. So they put it like very, very far away. So all these distortions are minimized in a way. But we cannot do that obviously when robots. So we have to think about other possibilities. For example, we have this Artemis is one of our rovers. He has like six wheels that also can change in his axis, as you can see here. And obviously that can be a lot of distortion to the magnetic magnetometer. So we can see here a couple of examples. So we actually measured that with a magnetometer that was somewhere here. How it was distorted according to some movements of the wheels. This is a histogram, which we can also represent it in a 3D. So that was in this small case. And of course, depending on the complexity of the robot, how many degrees of freedom it has, the distortion is going to be different. So we have like 4 different robots here. That one, Bilal represented, that's Oscar, Artemis, and Charlie. And they have different magnetic signatures. And also, for example, we can see here that Charlie is like this robot with these legs and arms because it's simulating like a monkey. It has many distortion, so it's very difficult to get a clear measurement of the magnetometer. So how we can solve that? Well, first of all, there's the classic way that is called static calibration, but that's not really helpful because the only thing that can calibrate is all the. So what can do? Let's go through it. Is if we have multiple magnetometers in our robot, then can try to fuse them, so they align them and scale them and make some conversion, so they are together, and then try to calibrate the effects of soft iron. Soft iron is the ferromagnetic effect, so that the material doesn't create a magnetic field, but only when a magnetic field is flowing through, then it changes and distorts it. And then they had iron effect with this proper magnet or inductive magnetic field through electronics, for example. But if they are static, and we know them, of course, we can gather some data and try to calibrate them. And that is the classical way to do it. Of course, that is not going to help a lot when we have a magnetometer close to the thruster. And that is actually here the case. For example, we have this magnetometers here, and the blue one is very close to this thruster. And when we're gathering the data, we can see how much it distorted actually the measurement of the blue, but actually the other ones. You can also see that the more close we are to the thruster, the more distortion we have. So we might want to make a dynamic calibration. Also, a simple way to do that might be only to have a probabilistic filter. For example, one that in our case has provided quite good performance and is quite fast to use is from Mises Fission distribution with based on stochastics, and has also a preliminary kappa, which you can tune, and there is methods to tune that depending on your position of the magnetometers and your AUV, so that at the end you can filter out this high distortion. So the orange one would be the average of all those the 5 sensors, and the green one is the filter one through this method. It's still not like the ground truth that is measured by the gyroscope, but is much better, definitely. But we can do better, right? So the thing is, we actually have a measurement of the RPM of the thruster. So that is like a preperceptive sensor, let's say, in our thruster, which we can measure how much RPMs we're giving right now. So we can use that also to calibrate. That is what Leif Christensen did in his PhD. And he did this experiment where we have these plates, and we have the main elements that can distort the magnetic field. And for example, this here, there's a electromagnet, which we can, through current, create more magnetic field or less. And here we have the shape that we gave. Then we have this movable mass, which is a ferromagnetic element that you can put it closer to the magnetometer, which is the 4 here one, or far away. Then you also have the like a cable, which can induce some magnetism through current as well, which is very close to the magnet. So here we have, for example, a snippet of the different data sets that we recorded. In this case, since this is a plane, we will have measuring different headings with different configurations to try to explore as much of model space as possible. In the same way that Bilal did, for example, with the Davon and the sinusoidal forces on the thrusters, to have as much data as possible to make a nice model. So these are the measurements for 3 different headings. And of course, here you can use different methods. There are different methods. The simplest one would be, of course, what also Bilal used, SVRs, support vector regressors, and also MLPs, so multi-layer perceptrons. Since it's not a very complex model, we tried both. And since the multi-layer perceptrons can also couple these effects for the X, Y, and Z, and also all the sensors, it's much more flexible. So at the end, it performs always better. And we figured out that it doesn't have to be a huge model. So we can also use some methods to measure uncertainty. For example, ensemble, which is a method where you have multiple models that are equal. So the model is not equal, but the architecture is equal. And then you train them. And since the randomized initialization of the values are different, and the stochastic learning process is different, the values would change a bit. So with that, you can then make a prediction with the 3, for example, models that you have, and make an average, which is your n prediction, and also get the standard deviation. So it gives you then a feel of uncertainty of the model itself. So as an example here, we did with this data. So we can see that actually where, go back. So here is withering, and here is only the error. So we see that where the peaks are is where our model is actually more uncertain of the measurement. And that's actually very useful information for and more in some when we are talking or something, that to say to the controller or the Navi filter, hey, we're giving this data, but we're kind of uncertain about this. There are also other methods, like for example, Monte Carlo dropouts. And I will put some articles on the references, which you can check out from some of our colleagues that are working with that. Quite interesting. Yeah, here, for example, when we already have the model, we can then definitely compensate the distortion that is dotted with blue, so that at the end, all the measurements are very centered on a point. That's actually what we want. So we can use the same method in robots, of course. For example, we did that with Sherpa. TT is this rover that is made also for space to make exploration on Mars. And you can see that it has many, many degrees of freedom, not only because of the wheels, but also every wheel has his own arm, let's say, manipulated to change and trying always to have the base stationary. So that can always go through all the craters and whatever terrain that you find in Mars. Yeah, so we use the same. Here you can obviously see the SVRs. We also try that. And also the MLP, and MLP performs actually the better. So I have some results. I will also put the paper with this work on the references. So now we have the static calibration and the dynamic calibration. So now we want to use it for localization, right? So how we do that and how we are starting to do that? Well, we have the black basin with a crane, which we can make. Well, you have to think that, yeah, so the idea is, go back a bit, that the docking station has a kind of a structure, or with soft or maybe hard iron effects, which we want to model. So we want to learn, like if we move around all the positions around this docking station, we should learn how actually is the docking station distort the magnetic field, and therefore find out the magnetic signature of it. Example we could do here, we have this structure, right? Also we have the marker to have the ground truth. And we move with different trajectories around marker and gather some data to try then to figure it out with MLPs, or also support regressors, the model, and to try to localize ourselves, which the predictions are quite impressive and quite good. So we try that also with our AUVs. And in the first test was quite good. We make 10 different runs, and at the end, it looks at supervector regressors in this case perform better than MLPs, and that is because they can generalize better. But we want to keep some more experiments and go in that direction for the project. And we see that at the end, we have like an error that's staying below 10 centimeters. And actually, the idea is that the closer you are to the docking station, the more, the better accuracy you have. In the opposite to all the other systems, right? So as Bilal mentioned, markers and acoustics and all your navigation system like USBLs and DVLs, the closer you are to the docking station, probably it's going to have worse accuracy. But in this case, you will increase it. So that's what is good for it, and good to try to have a combination of all these navigation sensor modalities, let's say. Okay, I don't know how I'm with the time. Can I go 10 minutes excursion to underwater perception, Bilal?
Yeah, go ahead.
Okay.
If people are not so tired, I think might be also a little bit interesting, since like not any more equations or mathematics, it's just like some insights. So
yeah, exactly. It's like more what kind of methods are there, what we're doing on the project. That's an interesting project that we started 1 year ago, and we do it with Pilar together. And what is interesting about it mainly is that we're going to gather a lot of data, also creating methods for underwater perception, which is a kind of niche. Not a lot of people is working on that. And all this data is going to be public, and you might use that for your PhDs if you need that. So I think that might be interesting to follow what we're doing. And yeah, and definitely maybe use the data sets that we are going to record. So first of all, what is multimodal learning? I already mentioned we want to try to do, right? So we have cameras and sonars, and they have the pros and cons. So we want to fusion them to try to have a better perception underwater. So sensor modality as a definition, well, is different means for perceiving the world. And when we have a multimodal system, like us humans, we have different sensors to perceive the world and to try to describe it in that way. So we can see, we can hear, we can taste, we can smell, and also we can touch, right? So we are multimodal systems to perceive the world. And multimodal learning, it means that we integrate all these different sensors and somehow we fusion them and work with them to try to have a better prediction or better understanding of the physical world. Why is that beneficial? That's kind of obvious. But I would put a couple of examples so we understand that better. Of course, sometimes we perceive with different modalities, for example, seeing and hear is supplementary and redundant, so it makes the prediction much more robust. So, for example, if I see an object on the sky, I might not know if it's a bird or a plane, but when I can hear the sound of a plane, then I definitely can say, oh, it's a plane, what I was seeing. So it's like makes my prediction more robust, let's say, because I'm fusing these two modalities. Also, can give complementary information that not only with one modality we understand, but I need two to understand that. For example, if the plane is on the ground and the turbine is moving, then I see the turbine is moving, and then I'm starting hearing the noise of the turbine because, yeah, chances of pressure that is producing. And then I can understand, okay, actually the sound that I'm hearing is because the turbine is rotating. So it comes from there and it has like a correlation. This correlation is also important. Of course, I can also predict one missing modality from existing one when I have this understanding. And that's, again, the example of the sky. Maybe I hear a plane and then I look up and it's cloudy, so I cannot see the plane. But I know that there's a plane there. And even since I have 2 ears, I can even position somehow where the plane is. And even I can notice if it's going towards me or going far away from me because of the Doppler effect. So there are things that you can, because of the previous understanding that you create with this multimodal perception, you can use it afterwards, even when one of the modalities is missing. So that comes with obviously challenges, and the algorithm should cope with. First of all, we need a unified representation because every modality comes differently. So for example, cameras has a 2D image, but sound could be only one the value in time. So definitely it's different, and also maybe letters or whatever we're using. So we need maybe to have a unified representation. So extraction of features, maybe one of the ways to go. Then maybe we want to fusion, first of all, the modalities to create something more interesting. For example, we might fusion 2 view of cameras to have a deep map instead of only RGB image. Translation, what I said before, so what we actually mainly trying to do in the project, well, could be like from the sound of the plane, for example, try to localize it on the image or whatever. Or create, yeah, if you hear something, you create maybe an image, generate an image that is according to what you're hearing. Then you have a problem of alignment. Normally, might be that your robot is gardening, for example, the perception of the physical world at the same time, but maybe not, for example. So it's not paired what you're getting, and you have to pair it through algorithms, for example. That might be in space or also time, and that's why there are some algorithms to do that as well. And co-learning is interesting, where in the training phase, and this is more for machine learning, we use, for example, a high quality sensor to train a low quality sensor that's going to be used afterwards during interference deploying time. So going a bit about the algorithm, what we're trying to do is generate a realistic visual-like image from the sonar image in low visibility conditions. And that is mainly because our use case is about divers that are working underwater, and they are doing different tasks like welding, cutting, sawing, because they are like technical and humanitarian relief team. And they should be always monitored by an operator that is up out of the water. And if something is happening, then should send somebody to help, right? And that's why it's very important to see what is happening, what's going on under the water. So the idea could be to have an AUV that's monitoring everything. But of course, all these operations might create a lot of distortion on the image. So you cannot only rely on image, so you should use also sonars. That's actually the idea. And what we're doing, for example, in the basin is gathering some data with divers. For example, you see the diver here. That's a very low resolution sonar. We got a better one for the next session. But yeah, by now we're working with that data. That are the clear images that we're receiving from top. We're also working with one partner that has his own laser scanner, which produces a very nice cloud images, which you can use afterwards as well. So the idea is you train with that, and then during the amphibians time, you have the unclear images, which is more common. And you try then to, with the sonar, that is not disturbed through these effects, try to get a nice image out of it. So the operator knows, okay, I can see the diver, I know how good he's doing. There are some bonus codes, which might be interesting because we're also developing that with sonar images, and it's, for example, detection. So we're using common detectors, like fast N CNNs or the YOLO, which you can see here on the image, but also single shot detectors. And we're trying then to find where the diver is. So we have the bearing and the position, which is a very valuable information. Also then, if we create a very clear image, we can even then also have body pause. So how we want to do that, in our basin, we have a tracking system, which we can also even track the joint and position of the body, pose of the diver. So we publish also these data sets. And yeah, we want to try maybe with sonar or with this realistic visual-like image that has been generated with the neural network, and use other typical algorithms that are out there. An interesting thing that we saw is that when the divers were using some tools, you could see also some distortion on the sonar, and we wanted to use that even maybe to identify the tool that he was using. So that comes with some challenges we have to also cope with. For example, we know that sonar data is very noisy, and also we have not much data. It's not like we have immense data sets like in image related machine learning data sets that are out there that we can use. In this case, we don't have those. So we have to try to cope with that. That's why we're working also with self-supervised learning. And also we want to interpret, so know how uncertain is this generation of the image, to give that information to the operator. But in the same time, maybe to the AUV. So when he's seeing, for example, that the uncertainty is very high, it might move around as an active operation and trying to get a better shot of the scene so we can help better the operator autonomously. And of course, everything has to be in a PC in the AUV. So we're coping with real-time interference on the robotic platform. So we have to also cope with model compression, like pruning, sparse representation, and quantization. So I'm going to go briefly to the methods. It's a bit long. So mainly what we want to do is fusion the sonar and the disturbed image and try to create a much clearer image, right? And what we're using is mainly GANs. I don't know if you know GANs, but it's mainly two neural networks, the generator, which normally through noise is creating an image, and the discriminator, which then took this image and should say if it's false or real, so it's a fake or real. And the way to train that is that the generator has to try to fool the discriminator by generating a very realistic images, and the discriminator then will learn with the generator in the same time, in a way of adversarial way. And it has shown a very powerful tool it can create a very realistic generation for the different generative models. In our case, we're using the conditional GANs, which is a bit different. So we are not giving a noise. So we give him something that he has to translate. So the generator has to translate to something that the discriminator should know. And the way to train also the discriminator is to give him also this input. So he should know that with this input should come this output. And it's like this train in the same way in the case of real ones. Some tricks of Pix2Pix is that it's using UNet, maybe you know it, for image segmentation, where there's also skip connections, so to try to get more realistic images at the end. And also using patch GAN or Markovian GAN, which means that the discriminator is not only saying it's fake or real, the whole image, but only fragments of the image. So here we have some outputs, and it's quite impressive how good the output is related to the real image, although the colors are not the same because, of course, the input is not giving any intuition of what color is that, but the realism of the output image is quite incredible. Some application underwater. Actually, the first one was in 2019, and that was in a fishing tank for aquaculture, where we have a sonar here and a camera, and they're trying to do what we want to do as well. So kind of similar. What they want to do is that they want to control the fishes also in the night, and they don't want to use light because that disturbs the fishes. So they want to create from darker images from the night. Using a sonar, they want to get daylight images. This was quite impressive, and that was kind of inspiration for this project and for the methods that we're applying. You can see them here. So that's not only darkness, but also they blurred a bit the image. And we see that actually with the sonar, you can recreate the image at the end. And only without the sonar, obviously, you have a mess. You can't see anything. But definitely it's doing something. So we already gathered some data, and we already trained it. So we apply actually the same method with quite good results, even 95%. Of 100 we're still struggling, but we have some ideas how to do that. And here we can see that the sonar is really giving some help, so to speak, for the reconstruction. And one of the problems that we have is that the sonar is with very low frequency, so doesn't have high resolution, but we're gonna use another one. So we hope that the data is gonna be better. The results. All the methods is Pix2Pix HT, which is only an extension of the one before. So the one before was here. So the extension is that to try to create or generate more high resolution images, you have to extend or create separate neural networks that is going to be trained afterwards. And that why it have to be afterwards is, but if you do it directly with high definition images, the generator and the discriminator, it doesn't really converge. And that's might be a problem. So normally you do it stepwise, and that is also inspired progressive GAN. And that's a technique that you can use to create more high definition images on outputs. Another interesting thing, so till now, we always need the pair image, as you imagine. So we have the contour of the shoe and also the image of the shoe at the same time to train. Sometimes we don't have that, right? So sometimes you don't have a pair image. In this case, we want a generator, for example, that translates a horse to a zebra. And you're never going to have the same image of a horse and a zebra, obviously. So you cannot use the same technique, right? So that's why it comes cycle GANs, which is very interesting in the way that what you train the discriminator is that you don't have to pass the pair image like it was in Pix2Pix, but you pass other ones. So the discriminator will understand, okay, that are zebras. So you generator better give me something that looks like zebra, but otherwise you cannot form it, right? And it's called cyclic GAN because you can do this process in the other way around. So you create from a horse a zebra, and you train the discriminator, but then you can also create another generator that creates from a zebra a horse. And this horse will have really the ground truth. So you can use then cyclic consistency laws to train those and to make a better generator. And then at the end, you have two generators that you can use to make this forward and backward transformation. Here are some of the results, and mostly this is used for style transfer, which means that you have for maybe an image and you want to have another style of it, like art of Koch or Monet or other kind of art. Why is that important for us? We want to use it for data augmentation because we have clear images and we want to transform that to a clear image, more real images that we want to use for. And since obviously we cannot get that with turbidity waters because we make a picture with clear image, we can use cyclic GANs to cope with that. But also it's interesting, maybe for you guys, some of you, which use synthetic data, which normally it's not really realistic. But with this approach, you can create realistic images or realistic sonar images, which you can use afterwards to pre-train your models and then do transfer learning, maybe less data. One of the problems with cyclic GANs and Pix2Pix is that you use it only one image and not the stream, right? So you can get some artifacts, like for example, this horse. Okay, one image, it looks like zebra, but the problem is it doesn't have time consistency. And that's why it comes bit to bit on play, which then the inputs also a sequence of the outputs we had before, and also some other tricks. Here's the paper if you want to look it up. And then you have really consistent, and there's no that kind of artifact. So that's something that we can do because we have a robot that makes a stream of images. Here are all the impressive things that you can do, might be related to what we're doing with the divers. For example, from an input, you can then extract the poses or dense pose, for example, and then with the dense pose, you can create another, make this style transfer. In our case, we still want to do the same. So we apply that to this fish monitoring dataset, and you see a better performance actually, but also in our dataset that we had before. So it has this consistency creates a better translation and enhancement of the image than before. So that's definitely help us to do that. Then quickly, I will go through self-supervised learning, which I think is a very interesting topic.
Maybe if you could like go through it, a little bit fast and to try to wrap up.
Done. It's only that. I mean, self-supervised learning actually is only like transfer learning, and the problem that we have in underwater is that we don't have huge data sets of sonars. So mostly we might have a lot of unlabeled data in sonars. So with self-supervised learning, what we can do with that is do transfer learning. So we can try a pretext task with the unlabeled data, and then transfer the part of the decoder to our target task. So we have some labeled data that's much less than our unlabeled data, and then with this way we can have a very good model even having very less labeled data. So it's one of the aims that we are trying to approach as well here, because unfortunately underwater we don't have much huge data sets that we can use out there. There are different pretest tasks, generative based methods, which I try to translate to generate from this to this, or super scaling, or from blurring to not blurring and that stuff. But also in streaming, try to generate the next frame, so you can also understand then kinematics of the movement. Also spatial context methods like only rotating the image and try to predict which rotation you are right now. Or also the jigsaw puzzle, which you change the puzzles, and the neural network should then predict the sequence of it. also in temporal context, so with videos, then maybe you can also shuffle the frames, and the neural network should then understand the sequence of the order. And that gives the neural network not only understanding of the human, but also understanding of the movement of the human that is doing on this action, which then you can transfer that to your target task. So that is some results what we're doing with one of our master students, and we will go forward. By the way, there's also these data sets which are available in case you want to use it. So thank you very much. Sorry, it was a bit too long, I guess, but I hope it was interesting.
All right, thanks a lot.